Greetings, I'm Professor Sever. Today we're going to consider analytical techniques regarding two important trigonometric theorems, namely the limit as x goes to 0 of sine x over x and the limit as x goes to 0 of 1 minus cosine x over x, whose limits are 1 and 0 respectively. Okay, so let's look at a problem. Suppose we were given the problem to evaluate the limit as x goes to 0 of tangent x minus sine x over x cubed. So in our analysis we see that we cannot evaluate this limit by functional evaluation, since the denominator, when evaluated at 0, would be 0. And this would prohibit us from evaluating this function at 0. Of course, the numerator is also 0 there, as the numerator would be tangent of 0 minus 0, which is 0. So this gives us some hope that the limit will in fact exist. At this point, since we have 0 in the numerator and 0 in the denominator when considering the limits of those two expressions separately, we don't know whether the limit would exist or not. So we have more work to do. Our first thing we might consider is to replace tangent x with what it is. We know that tangent is sine over cosine, so let's do that as our first step. And as we make that replacement, we see that we have a complex fraction, and in the numerator we need to simplify by getting a common denominator. Sine x is itself over 1, and so the common denominator between 1 and cosine is cosine. So we multiply sine x by the number 1, which is cosine x over cosine x, to get a common denominator so that we may simplify the numerator in our large fraction. Doing so gives us the following. And now to simplify, I will factor the sine x in the numerator out, obtaining sine x times quantity 1 minus cosine x divided by cosine x all over x cubed. We can simplify our complex fraction as follows. So we get sine x times 1 minus cosine x over the quantity x cubed times cosine x. Now, we can start to see some elements of our two favored limits that I mentioned, but they are not perfectly represented. So what we want to try is to imagine or consider, can we break this function up into several pieces where the limit of each of the pieces would exist. So let's consider this first simple separation, and we need to see, is it justified? The function factored as follows. Now the question is, can we write the limit of this product as the product of the two limits? Let's see. And now I have this step below. Now again, this separation, I'm writing it now, but I'm just using it for instructive purposes. We don't know that this is in fact appropriate. So, is it appropriate to separate the limits in this way? And in other words, the limit of the product is the product of these two limits. Well, this would be true if and only if the limit of each function, each of these functions exists. This one does. The right-hand factor, the limit as x goes to 0 of cosine of x is 1, so this would become 1 minus 1 over 1, and this limit exists and is 0. Well, what about this limit? Again, we don't know. It's not our favored limit of sine x over x as x goes to 0. It's close. It's sine x over x cubed, but we still have 0 in the denominator. And at this time, we can't say whether this limit exists or not. So, at this point, it's suggestive that this separation is not valid. Now I will give you a clue. This limit of the left-hand factor does not exist, and therefore this separation would not be valid. But in the event, we need to think of some different way, perhaps, to separate those two functions. So let's see. Now we know x cubed is x times x squared. Okay, so let's look at it this way. So now I have a triple. Right? I'm looking at the three separate functions, sine x over x, 1 over x squared, and the one that I already had, the rightmost factor, 1 minus cosine x over x. Are we justified in separating it into this triple product, as indicated? Well, we'll see the answer is no. But why? Well, the left-hand factor exists. This is one of our favored limits. This is 1 by theorem. We've already discussed the right-hand factor goes to 0, so we're fine. But the middle factor, the numerator goes to 1 as x goes to 0, since it's constant. The denominator goes to 0, so this is a problem. In fact, we know this limit of this middle term does not exist. That says this separation is not justified. And it would be a mistake to say 0 times anything would be 0, right? Because this is not a number. So 0 times something that's undefined, that's a nonsensical operation. So this separation does not exist. So we need to think about a different way to break this up. Again, assuming that breaking it up or separating the functions is the right thing to do, which in fact it will be, as we will see. So that was a spoiler alert. So again, we're looking at separating it thusly. This piece looks good. This is our favored trigonometric limit. Let's try to leave that alone. So the question is, what could I do with this x squared? Well, leaving it, matching it with the sine doesn't help. So how about I move it over with the cosine, 1 minus cosine term rather, and I'll move this term out as follows. Okay, so notice what I have. Now I have a triple product that I'm considering. Again, the left-hand factor is fine. We've already discussed it. It goes to 1. The middle factor now is fine. The cosine of 0 is 1. This would be 1 over 1, so the middle limit is fine. So now our attention is drawn to this term. Again, 0 in the denominator as x goes to 0, and 0 in the numerator. Still gives us hope that something may happen. Now again, we had the same comment a moment ago with sine x over x cubed, but we didn't really see how to proceed. Now, something comes to mind when we look at 1 minus cosine x. Okay, so now first I'm rewriting it to give us a little more space to continue the problem. We were down near the end of the page there. So now picking it up here, I'm going to multiply 1 minus cosine x over x squared times 1, and I'll choose as the number 1, I'm going to choose the conjugate of 1 minus cosine x over itself. So notice I have a 1 plus cosine x over 1 plus cosine x, and that's 1. Notice 1 plus cosine x is not going to 0. As x goes to 0, it goes to 2. So this would be going, this term in red would go to 2 over 2 as x goes to 0. So let's see what happens. Well, now again, nothing is happening on these two pieces, so I'll just continue writing these. And remember, every time, notice the good form here, you have to continue writing the limit at each stage of the problem, okay? Because we have not evaluated these limits. Now, you don't want to evaluate these limits yet, really, because we're not justified yet that separating it as we have done is appropriate, because we're still putting on hold this technique. And this is the way we work it. Strictly speaking, you could say it's not justified to do this. We should have gone to the side and on a separate computation worked this out to see if it would have existed. And then if it did, we could have transplanted in the work after the fact. But the way we work it, we separate now, we continue to work, and if in fact we can get a number that determine this limit exists, then it would have said separating it out thusly is justified. And this is the style in which we do these problems. So we do it knowing that we're not sure of this separation. Okay, so when we multiply these two terms, we can anticipate this is the difference of squares. So we're going to get 1 minus cosine squared on the top. And in the denominator, I'm just going to get the product of these two terms. I'm not going to multiply it out yet, because you want to just wait to see what happens. And if you're anticipating the trigonometry, we probably know that 1 minus cosine squared looks very familiar in terms of a Pythagorean identity. So let's do it. So we see on the next step, we get 1 minus cosine squared, and again I have the product of these two terms. So we're going to take 1 minus cosine squared. We know that's sine squared, so I'll make a replacement for sine squared, and you can replace 1 minus cosine squared with sine squared because they're identical. They're equal as functions. And I'll remove, for simplicity, this 1 plus cosine x. Where does it go? As x goes to 0, that goes to 1 plus 1 as 2. I'll move that out, separate it again, but rather than writing it as the product of 4 limits, which would be a little clumsy, I'll group it with the middle term, as you'll see on the next step. Okay, so again, the left-hand factor stayed the same. Notice what I did. I moved the 1 plus cosine x in the denominator out, but I went ahead and grouped it with this term, this limit. This limit still exists. Cosine of x goes to 1, and 1 plus cosine x goes to 2 as x goes to 0 in both of those cases. So now our attention is left with this, and this looks very familiar. It looks similar to this, but a squared in the numerator and the denominator. So now I can use the squaring function and continuity. You can use the composite function, but it's technically continuity we're using. And then I will write this as the square of the limit as sine x over x. Technically, continuity is being used here as well. So let's see what we get. And that's what we have. Everything stays the same. And now I have the squaring function passing to the outside the limit. In other words, it looks like the limit comes in and the squaring function comes outside. It's a composite function. That's kind of what's happening. And again, notice we keep writing the limit at every stage, and now we can see it. This limit exists. So it's 1 squared. And this was the factor. Actually, partially it was this. At this stage, we were concerned with the right-hand factor. We moved this component into the middle factor. We're not concerned with it. We're still concerned with the right-hand factor. It's a different right-hand factor now. And we see it exists. So now we know that separating it as we did was justified, because each of these 3 limits exist. Therefore, the separation was justified. The separation into the product of those three limits was justified. So moving forward again, just saving space. This is where we were, this step right here, picking it up from here. We evaluate. The limit as x goes to 0 of sine x over x is 1. We evaluate the middle term by functional evaluation. So we just plug in 0, which is what I've shown here. I'll evaluate that on the next step. And again, we evaluate what is the limit as x goes to 0 of sine x over x. That's 1 by theorem again, so that's just 1 squared. And again, this is what we have. Simplifying, this is just 2. In the denominator rather, this is just 2. Let's see that. Cosine of 0 is 1. 1 plus 1 is 2. 2 times 1 is 2. So this whole term becomes 1/2. And that's what I have. Finally, we multiply 1 times 1/2 times 1 is 1/2. And we've done it. We have evaluated the limit. And for completeness, I present the entire computation below.
Also, as a bonus, I have presented the computation in a more streamlined manner. It's presented next. Please review it. See if you can detect the difference in style in the presentation.
I hope you enjoyed this problem, somewhat involved, but with a little perseverance, we made it through. And again, we saw perhaps how not to try to break the problem up. So this problem was very instructive. I hope you enjoyed this video. Please look for my next video in this series. Thank you very much.